So, hi everyone, welcome to this session on problem solving through programming in C. So, this is an extra class that I've been taking for this session. So, let's wait for a few minutes so that people can join. Then we'll start the session. So, hi everyone. It seems none of you have joined the session. So, I will assume that you guys are watching the tutorial session on YouTube, right? So, I will just proceed as if the you guys are attending the session, right? Right. So, let's start. Right. Let's first finish up the problems. Let's continue from the previous session, the session that I had yesterday, right? Mm. So, mm, right. So let's, yeah, fine. I think, yeah, the session will be recorded. So please do attend, do watch the video, right? Fine. So this is April 7th, April 7th, 2026. So in the previous session, we were solving this problem where we used polynomial interpolation to find the value of y at equals to 2, right? And then in the next problem states, we have to repeat the problem using Lagrange interpolation, right? So what I will do is I will go ahead and reopen the solutions from the previous session, and then we will start comparing the solution that we get using polynomial as well as the one which we get after using Lagrange interpolation, right? So let me open up the solution from polynomial interpolation, right? So these were our data points. So the data points were for x equals to 0, y was 1 for that function. For x equals to 1, y was 2. For x equals to 3, y was 5, right? And for x equals to 4, y was 10. Then what we say in polynomial interpolation, essentially we approximate the function using polynomial functions. So, and if you pay a bit more attention on how this works and how can we, what kind of polynomial should we use? So we can use the general expression for a polynomial of degree d. For a polynomial of degree d, we can write the polynomial as this. So 1 plus ax plus bx squared plus up to k into x raised power d, right? Now, so the total unknowns in the polynomial function is, so essentially what we want is, so let's say this is our polynomial function. Then the goal of polynomial interpolation scheme is goal being goal being that for the given set of data points, p of 0 is equals should be 1, p of 1 should be equals to 2, so p of 3 should be equals to 5, and p of 4 should be equals to 10. So we need to find a polynomial such that these conditions are holding, right? So can we find these polynomials? Right. So we have 4 data points. Thus, we need a polynomial of degree 3. So we can, uh, yeah. So we can, yeah. Here I'm missing one information. It has to be a naught here, a naught here, right? So we have to use a polynomial n minus 1, where n is the total number of data points given, to find a correct polynomial interpolate, right? That passes through the given data points, right? So if I think of this, the solution to this problem would be like this. So you simply plot your data points. So 0 comma 0 comma 1, 1 comma 2, and then 3 comma 5, so not here, and then 4 comma 10, so not here. So my polynomial should go something like this, right? So this kind of curve is a valid solution. So what I can do is, so we have these four conditions, we have these four constraints. Let's choose a degree 3 polynomial and try to fit over these given data points. So the degree 3 polynomial can be written as p of x equals to ax cubed plus bx squared plus cx plus d. Now you use these conditions, right, and put them here directly. So first condition says p of 0 equals to 1. So if you set x equals to 0, you get y value to be 1, right? So this gives you first condition, statement, first equation. Then you choose x equals to 2, x equals to 1, and the y value has to be 2, right? So you put in the equation, get the second. Similarly, put in the third and fourth equations here, and you will get four equations and four unknowns here. So unknowns are a, b, c, d. Now you can solve this linear systems of equations, and we saw that the solution that we get is essentially these values of a, b, c, d will give us the correct polynomial, right? So yeah, so this was it. Now let's plot these results, and then we will see what other kind of interpolation we can use, right? Pratik ji, so we can plot our polynomial as y is equals to 1 by 4 x cube minus, sorry, 1 by 4 x cube minus 5 by 6 x square plus 19 by 12 x plus 1, right? So this was the result that we obtained. Let's plot our data points also. So let's create a list on Desmos. So the set of x values are 0, 1, 3, 4, right? Similarly, let the corresponding y values are 1, 2, 5, 10, right? And then I can plot my set of data points. And then you can see all four data points pass through this polynomial curve, right? This is the expected behavior that we wanted using polynomial interpolation, right? So the red line shows our polynomial function that we fit obtained by using these data points, and the blue dots are the uh, data points that we needed to fit. Now let's say if I want to find the value of x equals to let's say what 2, we can get the value of f of x, right? Right. Then we can get the value of f of 2 here, right? So now we can use t in fact, and we can choose any t between 1 to 0 to 4, right? comma f of t, right? You add a slider for t between 0 to 4, right? Right. So you can see this green portion represent our polynomial function. For each t between 0 to 4, this function works. Yeah. So we right. So the green part shows our the interpolate function or the violet. Let me make it. Yeah, the violet. The green part shows our green curve shows our interpolate function. And whenever you have a function f of x, you can always find value of x for any given t, right? So, right? Hello. Yeah. Okay. Right. So now if you change t between 0 and 4, so here you can see this green dot here, right? Green dot with a hollowed green circle around it, faded green circle around it. So as I change the value of my t from 0 to 4, right? 0 to 4, you can see my function stays on the curve. So I can find the function value for any x, right? So in between, so let's say I want to find the value of f volume function at 2 for t equals to 2.3, I can get the values, right? So at t equals to 2, the function value is 4. For t equals to 2, the function value is 2.833, right? Similarly, for t equals to 2.7, you get 4.12. So yeah, this is how you can use polynomial interpolation to generate fit a polynomial function for a given set of data points, right? Now, the next problem that we have to solve here is uh, yeah, share screen. The next problem is we need to solve the above problem using Lagrange interpolation, right? So again, let's go back to our notepad in our tab. So now let's copy my set of data points. So I think few students have joined. So am I audible? Anyone please confirm by typing in the chat box. Am I audible? Please confirm by typing in the chat box. Hello. So this was our data. Right? Again, we want to use Lagrange interpolation for fitting to this data, right? So basically, Lagrange. I hope I am audible. No one is responding, so I'm not sure what is the issue. But yeah, fine. So let me check once. Okay, fine. So now the next thing we want to use is we want to use Lagrange's interpolation here, right? So we want to use the Lagrange's polynomial to fit to these data points. So let's see how we can use this. Yeah. So the Lagrange's. I think I received a message from someone. Yeah. Fine. So let's. Yeah, so Lagrange interpolation says you can fit any function, fit a polynomial using Lagrange's fit a set of function, set of data points using an interpolation function that is a Lagrange's that uses Lagrange's polynomials, right? So your Lagrange's in the basis of Lagrange's polynomial, right? So the interpolating polynomial can be given as a linear combination, which is given by j equals to 0 to k yj lj of x, right? Where right, where lj of x is given as, so these are this is a combination of set of k basis polynomial basis functions, where k is the total number of data points, right? Sorry, k plus 1 is the total number of data points. So total for k plus 1 data points, or you may call them observations, right? So then Lij of x is given as product 0 to k m is not equals to j, and x minus xm divided by xj minus xm. Right? So basically what happens, why do we use this kind of polynomials? So essentially it allows you to do online interpolation. Basically you can keep adding data points. And the second use case of this kind of polynomial interpolation is the solution to the system of equations is very easy, right? So that's why we use Lagrange's interpolation, right? So these things have been covered in the class, I guess, right? Right. So let's start where xi, basically xm is the data point, right? Acha, this requires recomputing the entire polynomial, right? What? Yes, you will get a function that because in the denominator you have to product all the data points. So yeah, you need to multiply. Yeah, you need to multiply. So you need all the data points. Sorry, that was a wrong statement. Yeah, you need Lagrange interpolation. Uh, you need all the data points while using. You cannot use it in online fashion, right? Right. Hmm. So let's find the polynomials here. So we have four data points. Four data points. So we need to compute three polynomial, which acts three polynomials, which are the basis of this interpolant, right? So let's define. So yeah, so k, what k is? So fine. So k here is 4. Right, you first need to k equals to 3, right? K should be, let's see. L0 will be, so let's call it x0, x1, x2, x3, right, on the left hand side. So L0 would be x minus x0 by x, okay, x, x minus x, yeah, so x minus x1, because I'm talking about x0. So xj is x0 minus x1, right, multiplied by x minus x2 divided by x0 minus x2, right, multiplied by x minus x3 divided by x0 minus x3, right? Right. So this is how you write the Lagrange polynomial function, right? Right. So now this is your L0, then your L1 will be x minus x0 by x1 minus x0 into x minus x2 by x1 minus x2, right? Into x minus x3 divided by x1 minus x3. Similarly, the next basis would be x minus x0 by x2 minus x0, 4 bases here, into x minus x1 by x2 minus x2 minus x1 into x minus x3. Sorry. Wait a second. Okay. X minus x. Yeah, so this is x2, right? X minus x3 by x2 minus x3. Okay. Similarly, L4 is equals to x minus x0 by x3 minus x0 into x minus x1 by x3 minus x1 into x minus x2 by x3 minus x2. So this is L0 of x, the first polynomial. The second polynomial is L1 of x. Then So L0 of x is this polynomial, and 1 of x is this polynomial, and 2 of x is this polynomial, and L3 of x is this polynomial, right? So we have these four polynomial bases that we construct here, right? Right. And then, right, right. And then if you observe something here, for any LJX, so for any LJX, fine, for any LJX, LJ of XK K not equals to J will be always be 0, right? So for example, for uh, I think my screen is my screen is working. So for example, for L0x, if you put x equals to x1, right? If you put x equals to x1, this first term will be 0. So the entire polynomial will be 0. Again, if you put x equals to x2, then again your polynomial will be 0. And x equals to x3, then again it will be 0. So for any k, which is not equals to j, if you put xk in the polynomial Lj, the polynomial will return 0. Right? This is an interesting property for these Lagrange's polynomials, right? So this ensures that the four polynomials are essentially orthogonal in terms of this data points, right? So yeah, fine. So now when you have this when you have this Lagrange's polynomial, you can easily compute yj. So now we need to simply compute the final Lagrange's interpolation formula here from here, right? So we need to find this. So the unknowns Lj's are known here, right? So then what is yj here? So we know Lj from here, comma yj is equals to Lj of xj, right? So yj is very simple. So let's start computing yj here. So let's compute y0 is equals to L0 of x0. Let's put in the values. Let's start putting in the values and get the final answers. Right. L0 of x0. Right. Let me replace the values here. Right. Let me first replace the values. Right. This is so let me just highlight the important property from here and then can proceed. So this is one thing. So let's actually getting the polynomials here. So L0, the zeroth polynomial is x minus x1 is 0, x minus x2 is 1, x minus, oh sorry, x minus 1, x minus 3, or x minus 4 divided by the numerical values x0 minus x1 minus 1 into x0 minus x2, which is minus 3, and then minus 3, right? And then similarly y0 would be y0 would be L0 of x0, L0 of x0. So let's put x equals to 0 in the polynomial on the LHS, and you will get the value. So let's put x equals to 0. The y0 would be minus 1 into minus 3 into minus 4, minus 1 into minus 3 into minus 4, which is 1, right? So yj's are essentially ones, right? So from you can see here, right? So if yj is equals to lj of xj, so lj of xj is always 1, which is equals to 1, right? For all j. belongs to 0 to up to k, right? So we don't need to compute yj again and again, right? Now, so L0 is known. Now I can compute L1. Uh, and similarly, L1 would be x minus x0, which is 0, x minus x2, 3 into x minus 3 into x minus 4 divided by 1 minus 0, 1 into 1 minus 3 minus 2 into 1 minus 4, which is minus 3. Right? Again, y1 is equals to 1. Then L2 would be x minus 0 to x minus 1 into x minus 4 divided by 3 minus 0, 3 minus 1, 3 minus 4. So 3 minus 0 is 3 into 3 minus 1 is 2. So plus 1, right? And then L3 would be x minus 0, x minus 1 into x minus 3 divided by 4 will be 4, 3, 2. 4 into 3 into 4 into 3 into 2. Again, y2 equals to 1 and y3 is equals to 1. When you have these, you add them up to get the final polynomial term here, right? So now your interpolate function becomes, so that interpolating function you will get is L is equals to L0x plus L1x plus L2x L3x, right? Just add them up and you should get the same result as the you should get the same result as the previous as the result that you obtained using uh, this polynomial integration, right? So let's check if that's true. So okay, let's take this. Let's simplify all this. Right. Now this is 4 3 12 minus 1 by 12 into x cube. Wait a second. A plus B. A, B. Yeah, right. So the equation would be x cube plus a plus b plus c into x squared. Those four three subchunks, so they count. Minus 8 x squared plus 3, acha, ab. So 3 plus 12, 3 plus 12 plus 4, right? So, okay, plus 19x plus 4 to the 12 minus 12, right? Right. So this is your first term. The second term would be 1 by 6 into x cube plus a plus b plus c x squared. So 7x squared 0 12 0 plus 12x ABC, right? So this is your second term. The third term will be 1 by minus 6 into x cube a plus b plus c. So it will be plus 5x squared ABC, AB, BC, 4 plus 4x, right? Similarly, this will be 24 x cube a plus b plus c minus 7x squared 3 plus 3x, right? So just add them up to get the final function here. So let's take LCM 24. uh, Let's add them up. So the equations were that you just need to add these equations and you will get 1 by 24 into, right, minus 2 plus 6 6 4 minus 4 plus 1, this into x cube, the same thing into, right, plus minus 16 minus 20 28 plus 20 minus 20. Yeah, signs are same. Minus 20 minus 20. Okay. Wait a second. Yeah. Okay, I messed up the signs here. So let me correct them up, right? So you'll get 12 to the 24, right? So my minus plus. So 16 plus, again, this is minus plus minus 7 for the 28. Then minus plus 5 for the 20 plus minus 28 into x squared plus. Okay, so I think now you guys know how to come up with the solution. But when you solve this, you will see that this will be equivalent to the polynomial interpolation formulation you get, right? So what was, let me just bring up the result here. So this will. So the results using your Lagrange interpolation and your polynomial interpolation will be same. Right. You can do the algebraic operations. So you'll get the same curve, right? So this is the final answer. So yeah, the result that we were seeing was correct, right? So you will get the same behavior. Fine, everyone. Is this clear? Any doubts? Please type in the chat box. So you will get the same curve here. So you'll get the same curve for the interpolation, right? So the only difference is how you are computing the polynomial function, right? Someone is typing in the chat box. Do you have any doubts? So someone is trying to type some answers, questions. I am not getting them. Right. So I will take up the query later on. I think there is some network issues. Right. So let's move on to the next question. Oh, okay. So we already saw the code for this interpolation, right? In the previous session only, right? So, yeah. So the next concept that we did not cover in the previous session was use it was basically computing the integral of a function, right? Of a given function. Now, let's say you are given a function e raised power x squared, and you want to find the area under the function between for x between 0 to 2, right? So now we move on to integration problems, right? Essentially quadrature rules, and we will see a very basic example of quadrature, right? So quadrature, right? So let's say you are given a function y is equals to f of x, and you want to find the integral for x equals to 0 to x equals to 1 f of x as x varies dx, right? So if we plot the curve for this function, right? So this is the x-axis, this is the y-axis, right? Now what I can do, let's say my function looks something, my function is f of x is x squared, y equals to x squared. So my function will look like this, right? So for x equals to 0, value is 0. For x equals to 1, the value of y will be 1. And this integral essentially represents the area under curve in this region, right? So area under curve in this region. So everyone please hang on for a minute. I have some right? So sorry for that. So let's resume. So yeah, then this integral essentially represents the area under this curve, right? So this area, the integral represents the area under the curve. Now, let's say I am giving you very simple function such as f of x is equals to x squared. So you can very easily compute the area under the curve for the given range, right? So just use the integral formula. So we actually know the integral is essentially so you can use the antiderivative formula for this. So we know that integral of x raised to power n dx is the integral x cube by 3. So x raised to power n by n plus 1 by n, where and take the values from the limit range in the range for x equals to 0 to x equals to 1. Now this becomes 1 cube by 3 minus 0 cube by 3, right? So the area under the curve is 1 for this given particular function and under this range for x equals to 0 to x equals to 1, right? So this is very easy, right? You can do this very easily, and then you get the area under this curve. Now there is one issue though with this method is there is your dependency. There is a dependency here. There is a dependency that the function must be integratable, right? Right. So which are non. So let me give you some example on non-integrable smooth functions. So, yeah, it has to be integrable. Yeah, sorry, it has to be integrable, right? So why I'm saying this, because we already have seen this in class intermediate maths calculus lectures, but again in those scenarios, what we were given some fixed set of functions. For example, you know the integral of f of x equals to x raised to power n, and what is the integral of f of log x, and so on. But yeah, in general, we don't have any general formula for any kind of function, right? So we'll see one example here, right? Right. So we will plot the function and we will see that. Uh, right. Right. So if you choose a function like this, f of x is equals to 1 e raised to power minus x squared, then you can't find the integral of this function to 1, right? So x squared dx very easily, right? So this is not straightforward. So for this, you might need some sort of quadrature rule, right? You will need some sort of quadrature rule. right? So how to integrate this function, how to find the area under curve for this function, right, everyone? So let's start with this. So let's first solve a problem using a quadrature rule for very simple case for which we already know the analytical integral integration value, which is 1 for the curve, quadratic curve here, right? And then then we can solve for these kind of functions, right? So let's start with the simpler case. So now the quadrature rule that we are going to use right now is trapezoidal rule, right? So let's start with the trapezoidal rule here. So let me first take the plot again and then show you the intuition behind the trapezoidal rule. This is x-axis, this is your y-axis, right? This is x equals to 1, y equals to 1, and you want to find the area under curve for this curve, right? So what you can do is you can split this curve into small curves, right? Right. You can split this curve into small, right? Okay. Right. So you can split this into small segments at equal distances on the x-axis, right? Right. Let me just erase this, and then you get this line, and then finally this, right? So this is x equals to 1 here, right? So when you look at these segments, right, they form small trapeziums, right? This function is made up of small trapeziums, right? So you divide the curve into small segments that formed by trapezium. And you can see the trapezium essentially, these trapeziums are essentially capturing most of the area under this curve, right? So more precisely, what we can do is to show a better reasoning for this is, right. Okay, sorry. Right. So let's say this was our curve, right? So now what I want to do is I want to find the area under this curve, right? What I can do is I can use the starting and ending data point, right? So let me just make the function a bit, shift the function along the x-axis so that it becomes a very easy case for you to understand, right? So let's make the function like this, right? Right. So this is your function, right? So this should y is, let's say, 1 here, right? So y is equals to x squared plus 1. So when x equals to 0, y equals to 1. And then when x equals to 1, y equals to 2, right? So now you want to find the area under this curve. So one very easy way to approximate this area is try to find the trapezium that fits these two data points, right? So you can choose the trapezium can be found by these lines, right? The green lines. So observe the green lines. And these are the two parallel edges of the trapezium. Then you can join the edges to form this trapezium. And then you can use the area formula for area is equals to 1 by 2 into sum of what parallel edges, right, into height, right. You can use this formula simply to compute the area of this parallelogram, sorry, this trapezium, right, which is essentially half into this height. This height is f of 0 plus this height is essentially f of 1, right? F of 1 into height is basically x 1 minus x 0, so 1 minus 0, right? So now you can use this approximation to find the area under this curve. But note that when you use this approach, you get some error. Now, thus that error is equal to this region, right? Area of this region. So this pink region. So you will get an error of sort of size this, right? Of this size. So this is your simple trapezoidal rule for this curve, right? Now, if you want to make this function, this trapezoidal quadrature, use trapezoidal rule to make the area under the curve more accurate, what you can do is you can again you can divide the function into smaller segments and then use the trapezoidal rule, right? So you don't use the entire big section, you divide it into smaller segments, right? So let me take a segment like this. Then so you divided this function into two segments. Now you get two trapeziums here, right? One trapezium here and the second trapezium here, right? So let's say this point was 0.5, this point was 0, this point was 1. Now you can see the error has reduced to only this much, right? From this much error, you have reduced to this much error. So as you increase the number of trapeziums while approximating during the quadrature rule, you can you will reduce the error, right? So so we all know the formula now for computing the trapezoidal rule, right? So how to devise the algorithm for this? Now we know the mathematics behind it. Now we'll be writing the code that implements this rule, right? So given function f of x, right? And total segments, so total trapeziums, right, that we'll be using in the trapezoidal rule is equals to n and uh, region region for integration, right, x0 comma x1. You can define the algorithm for this, so trapezoidal rule. So height, so now you will define height of each trapezium is equals to x1 minus x0, given x1 is greater than x0, right? X1 has to be greater than x0. If not, then swap them, right? X1, right? Height for each trapezium is this. And then you can define the total segments. Total segments would be height, which is h. Let's call the height as h. So h by n, right? So total segments would be h by n, and we will be taking, uh, yeah, we will be taking integral number of such segments, right? Right. So for the beginning, so what we will do, we will start, start the loop here. So I'm writing a pseudocode here. For I is equals to 0 to n. The total segments is already n, right? Total segments is given, right? Is already n. So height would be h by n, right? X1 minus x0 by n. So height will be h, which is x1 minus x0 by n, right? Yeah. Sorry, I made a mistake here. The height will be x1 minus x0 divided by n, right? The total sections. So basically, let's say your x0 is this value, x1 is 1, and you are choosing some, let's say, three segments. So you divide this into 1, 2, 3. So height of each trapezium is now h by x1 minus x0 by 3, right? So that's why we use x1 minus x0 by n, right? So for each segment, what we do, we compute x0 is equals to, uh, right, x, yeah, xa, right? Let's call it xa is equals to x0 plus I into h, right? And xb would be x0 plus I plus 1 into h, right? So these are x. Now I have a smaller segment xa and xb. Now I want the sum of parallel sides. So sum of parallel sides would be sum of parallel sides. So f of xa, f of xb, right? I can create a variable here, area, and initialize it with value 0, right? Now I can add the area for this trapezium. Area plus is equals to half into sum of parallel sides into h here, right? So now you keep adding up the area and you get the correct formation, right? So for example, for this trapezium, you had two segments. So height was 1 minus 0 by 2, which is 5.5. So for segment 0, you computed the area. Then for segment 1, you compute the area, right? And you repeat. So this is how you trapezoidal rule works. And now we'll be writing a code for this rule, right? Right. So let me share my screen. Right. So I'm going to write my code, hashtag include standard IO, right? And yeah, then my main function, and then return 0. So these are the basic functions. Now first I will create a function for trapezoid that computes the area of a curve using trapezoidal rule. So let's first define my function. Let's first define my function. So float f of x, and it takes a floating value x and returns a floating value here, right? And then you compute the result, double f double val is equals to function value, and the function we were interested in, x squared plus 1, right? So now what you do, return val, right? So now this is your f of x, And then I will write a function that computes the area of a trapezium. Again, the function returns a floating point value, area of, and let's call the name to be area of trapezium, right? And then I will take float side one, parallel side one, right? Again, float side two, and then float height, right? Then I can return the area, return half into side one plus side two into height. Okay. So this is the function that gives me the area of trapezium. And finally, I can write the trapezoidal rule. Trapezoidal, right? Right. So the trapezoidal rule function needs to know for which function you want to compute the area. So our function is f of x here, right? So you just need to find the number of, pass the number of segments, right? Right. So now here you can compute height. Height is equals to segments and the ranges for x0, right? So float x0 comma float x1, right? So now height would be x1 minus x0 divided by segments, right? So now you get the height here. Now for int I equals to 0, I is less than segments, right? I plus plus. For each segment, what you can do, compute. So let's create another variable area here and set it to 0, right? Now for each segment, you can compute the area of the trapezium, So side one would be fx at, so now I need to define f float xa. Xa would be I into height, right? Float xb would be I plus 1 into height, right? Now you can compute the side one length, which is fx of x, f of xa, then f of xp, and the height is already computed here, right? So this will give you the area. So you simply add it to the area variable here. And finally, you return area from this function, right? So this is your trapezoidal rule function here, right? We can use this to find the area of any function. So for example, the current function is x squared plus 1, right? So now in the main function, let's try to find the area between x0 and x1. So let declare x0 equals to 0, right? Load x1 equals to 1, right? Now I can call the function. Let me find. Load area is equals to trapezoidal rule. Area plus equals to. So let's use one segment first, right? Let's pass x0 and x1 here, right? So let's do this. Let's see the result here first. So printf area using analytical integration is percentage of. Then I will and for percentage these segments. Now I can say trapeze. Okay, sorry. Let's move it to the next line. Now printf the area using trapezoidal rule with percentage d segments is percentage f backslash n, and then also we will print the error, right? So the error is percentage f, right? So let's declare float correct area that we have already computed, which was x cube by 3 plus x, right? X cube by 3 plus x. So set x equals to 1. So 1 by 3 So 1 by 3. Yeah. So 1 by 3 plus 1 minus 0. So it is 4 by 3, right? The correct area is 4 by 3, 4 by D, right? So the area using a literal integration is correct area. The like segments is this, and area is this, and the error is STD fabs. Oh, sorry, fabs area minus correct area, right? So let's include math.h for fabs function here, right? And let's declare the number of segments here, right? So let's pass the segments variable here. Yeah, right. So now let's see the output, right? Let's run my code. And you can see the area using analytical integration is 1. The area, wait a second. Okay, yeah, this is wrong. So this has to be floating. Huh. So area using analytical integration is 1.333. But if you use 1 point trapezoidal rule, you get an error of 0.166, right? With one segment. So everyone, please look into this code and ask any doubts if you have. I'll be back in a minute. Fine, everyone, welcome back. So let's do another experiment where we change the number of segments. So segments plus plus, right? So now let's run our same experiment with the increasing the number of segments, and let's see if the error reduces, right? So let's just see the error here, right? You can see as we segments percentage D, so as we increase the number of segments, the area error decreases, right? So for first segment, you had area 0.166. For segment two segments, it jumped down to 0.04. For three segments, it jumps to 0.01 and so on. And for nine segments, it goes to 0.02. If I increase the number of segments further, you will see, let's see how small we can go. So it is of order of 10 to the power minus 5, right? So you can see we are almost able to capture the area of uh, divided by correct area, right? We need to capture the correct area, right? So we are able to approximate the actual area up to some precision using numerical methods, right? So this is the trapezoidal rule. So this has been covered in the week session, right? Right. So yeah, so it's already 7:30, and uh, if you have any doubts, please type in the chat box. Otherwise, we can end the session. So, hi everyone. So let's end the session. Thank you all.